Okay, in this question, we are analyzing a function. We're analyzing f of x equals 6x to the fifth minus 10x cubed, but only on the interval negative 1.5 to 1.5. So there's going to be a lot of different things that we're going to do. We're going to find our critical points. And remember, critical points are mins and maxes and sometimes points of inflection. We are going to find any mins or maxes. We are going to find points of inflection. We're going to find the global minimum, where it decreases, and where it's concave up. Okay? So the very first thing that I like to do is I like to put this function either into my graphing calculator or into Desmos on this interval and actually analyze what is going on. And so I've already put it into Desmos, and that's before I do any of the calculus. I know what things I'm looking for. I have kind of a checklist of things, mins and maxes, global mins and maxes, increasing, decreasing, concavity. So let's just look at this function and analyze. If you are trying to figure out how do I plug this into my graphing calculator, how do I plug this into Desmos, on Desmos, you're going to plug in your function like this. And then if you use the squiggly brace, then you can actually put in a domain. And what you'll notice then over here is that it actually stops at that 1.5, positive and negative, because I restricted my domain. Now that gives us a lot of stuff to actually look at on this graph, which is pretty cool. What I notice is that my absolute minimum is down here. This is my absolute minimum point. I also notice my absolute maximum point is right here. I notice that I have a max and a min, and then I have kind of this thing right there, which is probably going to be some sort of critical value, even though it's not a max or a min. I see that I'm concave down to start. I switch to concave up right here. Then I'm concave down, and then I'm concave up again. So I have 4 different types of concavity. I have got concave down, concave up, concave down, concave up, which means that I have to have at least 3 points of inflection. It changes concavity here, it changes concavity here, and then it changes again concavity about here. So just by analyzing this graph without doing any calculus, I have a lot of information. I have that my absolute min and my absolute max is not one of the critical values. It is one of the endpoints. I have that I have one relative max and one relative min. And I have that there are probably 3 points of inflection here. So let's go ahead and start actually doing the calculus of this. We will be flipping back and forth between Desmos and this problem. So A, use calculus to find the x coordinates of the critical points of the function, and then use your calculator to find the corresponding y values. So we're using calculus to find the x's, and then you always find a y by just plugging it into the equation. So to find the critical values of a function, oops, I guess I need to make it. So to find the critical values of a function, we take the first derivative and set that equal to 0. So the first derivative of this function, well, we can do the power rule. So 5 times 6 is 30. And then you drop 1 power, so x to the 4th, minus 3 times 10 is 30. And you drop 1 power, so now we're x squared. So we took the derivative. The next part of that is actually setting it equal to 0. So if I set this equal to 0, I have 0 equals 30 x to the 4th minus 30x squared. In order to solve this, we're going to need to factor. So I know that they have a 30x squared in common, which leaves me with x squared minus 1. This could be factored further into 30x squared times x minus 1 and x plus 1. Now I can very clearly see my critical values. Set each factor equal to 0. Each factor, this is a factor. When I set that equal to 0, I get 0. This is a factor. When I set that equal to 0, I get 1. And this is a factor. And when I set that equal to 0, I get negative 1. So I have 0, 1, and negative 1. Those are the x coordinates of these critical values. I like to put these in numerical order. You do not have to. It just makes it easy for me to see. So I've got my x coordinates of each one of these values. So now to find the y coordinates, you simply plug those values in for the x's here. Okay? 0 is easy. When I plug 0 in, it's just going to be 0. So I've got 0, 0. Now the other ones, I'm just going to go back to Desmos. And I can either click and it will tell me that it's 1, -4, and 1, -1 and 4, and 1, -4. Or I can actually type in f of -1. Is this one my negative? I don't know if this is, I think negative's over here. I'll just flip my screen really quick so I can find my negative. F of -1. And it actually tells me right here that the answer is 4. And then I could change this to 1. And it tells me that my answer is -4. So you can do it any way that you like, but that gives us our critical values right here. So we've got 4 and -4. In A, you are not looking at the endpoints at all. A is not asking about the endpoints. Endpoints are not critical values. Critical values are mins, maxes, or points of inflection. Okay, there we go. So B says use calculus to properly identify any local relative extrema or indicate if they don't exist. So we already know by looking at Desmos which of these is a min and a max and which one is neither, right? We already know that because looking at Desmos, this is clearly a max, this is clearly a min. But this question specifically says use calculus. So we can write our answer here because we know what it is. -1, 4 is a max, and it's actually technically a relative max, right? And -4 is a min, or technically a relative min. But how do we do this using calculus? Well, we have the second derivative test. And the second derivative test says that if the second derivative of the critical value is greater than 0, meaning that it's positive, it's a minimum. If the second derivative of the critical value is less than 0, meaning it's negative, then it's a maximum. I hope I have that right. Concave. Yeah. So, let's go ahead and take the second derivative. The second derivative of this function, we will go back up to this right here. Well, 4 times 30 is 120x cubed. And then 2 times 30 is 60x. Okay, so there's our second derivative. And now we can plug in -1 and we can plug in 1. So f double prime of -1, well, that's going to be 120 times -1 cubed minus 60 times -1. And that is going to be -60. This is a negative number, which means by our second derivative test, it's a max. And that's how you show it using calculus. Let's do the next one. 120 times 1 cubed minus 60 times 1. And that gives us positive 60. That's a positive, so this is a min. We do need to check that last one because we don't know that it's not a min or a max. I mean, we do because we're looking at this graph and we know that it's neither. So we know that it's going to be 0, but we do have to show it on here. So f double prime of 0, 120 times 0 cubed minus 60 times 0 equals 0, which means it's neither a min or a max. Okay, So not so bad yet. In the first question, in A, we took the first derivative, we set it equal to 0, and we got our 3 critical values. Sorry. In the second part, we wanted to state whether those critical values were a min or a max. So we took the second derivative, we plugged in the x values, and if it was negative, it was a max, if it was positive, it was a min, and if it was 0, it was neither. Now, these are opposite for a reason. The plus really means that it's concave up. So this means that it's concave up. And if our function is like this, of course it has a minimum. And the negative means it's concave down. And so if our function is like that, of course it has a maximum. And so if you're having a hard time remembering that, remember the second derivative actually tells you concavity. But using that concavity, you can determine whether it's a min or a max. Okay, so we're on C. Use calculus to find the x-coordinates of any inflection points. We use the second derivative to find inflection points. And so we already actually solved for the second derivative. It's right here. So now we just need to set that equal to 0. So 0 equals 120x cubed minus 60x. Let's factor out the stuff that we know. So we know 0 equals 60x times 2x squared minus 1. Set each of your factors equal to 0. So this is a factor and this is a factor. So this one is easy. That's 0. And we already solved that. That's 0, 0. We know that's 0, 0. Go back to your original. That is this point right here, 0, 0. Now we need to solve these ones. So 2x squared minus 1 equals 0. That's going to give us 2x squared equals 1, x squared equals 1/2, x equals plus or minus the square root of 1/2. This does not say exact. Do you see that? Nowhere in here does it say give the exact values. So let's go ahead and figure out what is the square root of 1/2. So use our fancy little calculator here, and we're going to say the square root of 1/2 is 0.707. And it's going to be plus or minus that. So we have x equals plus or minus 0.707. So use calculus to find the x coordinates of any inflection point. I guess we didn't actually need that y coordinate. So x equals 0 and plus and minus 0.707. Of course, you could keep that the square root of 1/2 or root 2 over 2. Any of those answers are going to work, but because it doesn't have to be exact, you can round to those 3 decimal places. Let's see if that makes sense on our graph. So as we go on our graph, we're saying at 0.707, that's where we're going to have this point of inflection. So 0.707, what is this, about 1/2 right there? So this is about 1/2. So yeah, that would make sense because 0.707 is going to be right around here. And look at that. That is where it would change concavity. That is where it would change concavity. And we already knew at 0, 0, it was going to change concavity. So I would say that that does make sense. Okay. On the given interval, list the coordinates of any global absolute minimum. So absolute minimum means what is the very, very, very lowest value. It doesn't say we have to use any calculus for this. So let's go back to this. The very, very lowest value is right here. So when I click on that point, it's negative 1.5 and negative 11.813. There is no value that's lower than that. So that is our absolute minimum. Negative 1.5, negative 11.813. Okay, over what intervals does the function decrease? Again, it doesn't say you have to use calculus for this. You've figured out everything you need to know. And so as we're looking at this, my function is increasing up to here, decreasing, increasing. So it's decreasing from here to here. You know what these values are. You figured them out. They're your critical values. That's from -1 to 1. So from -1 to 1, this function is decreasing. Now remember, these are open intervals, because at the point -1 and then at the point 1, it's not increasing or decreasing. It has a slope of 0 there. It's a min or a max. All right. And the last, over what intervals is the graph concave up? So again, it doesn't say using calculus. So concave up. So if we're looking at this, we are concave up here. And we know what that point of inflection is. It's -0.707, because we figured that out in a previous question, until 0. And then we're concave up here. And again, we already figured that out. That's 0.707 all the way up to infinity. Not to infinity, I guess. Actually, it's only concave up until the end of the interval, which is 1.5. So if you like to draw a little picture so that you know kind of what it looks like, let me check what that looks like again. It looks like this, right? Flattens out, goes down, and goes up. We're concave up here, and then we're concave up here. So that's from -0.707 to 0, and then from +0.707 to the end of our interval, which is 1.5, and that will be closed because we are going to hit at 1.5, and at 1.5 it is still concave up. So as you're working through this problem, just remember everything is coming off of that original function. What you'll notice is that when I was looking at Desmos, never once did I actually click on my derivative, my first and second derivative. I have them on here so that I could double check and make sure that I found the derivatives correctly, but all of the analyzing came from that original function. So you don't ever actually have to put your derivatives in here. Oops, I unclicked the wrong one. That's okay.